Joseph, it's recording?
Yes, it is.
Okay, what does this mean?
Not for all A. So for all A is not true.
No, not for all X.
Oh, not for all X. I'm sorry, guys.
Okay, guys.
So smart.
Using De Morgan's law, what can this be simplified to?
Wait, what is for all not of X?
No.
Wait.
Dude, saying that it's not true that all of the students did their homework doesn't mean it's true that all of them did not do their homework. That's totally different. It means there exists an X that is not true. So if not all of them are true, there exists one that is not true. That is De Morgan's law. This is like or, you know, logical or. This is repeated or, this is repeated and. So it's like De Morgan's law says these are equivalent. Or wait, no, that's like.
Oh no.
Wait, do you have any races?
Oof, you smudged the board.
Okay, so now I'm going to put up a couple of practice problems.
Oh,
Now, okay, so if I've already told you or you recognize it just because you already know the formula, don't say the answer, okay? So,
Wait, so don't say the answer if we know the answer?
Yeah, it's kind of
don't say the answer if you already know. These are actually established formulas. These are the definitions of things. So if you already know the thing it's defining, don't say it. I want somebody to figure it out just from the notation.
Wait, Eli. It's a problem with that. What if everybody knows the solution?
Well,
Nobody is okay, trust me, they won't fall. Okay, so I'm gonna say guys, order. We have to go fast today. Okay. So for all X and okay, I wasn't. Forget I said that.
For all X in natural
No, shut. Okay.
No, the N has
For
to
all
go
X in natural numbers.
It's not.
It is, I looked at it.
Oh yeah?
The bars across the middle.
Hey, where have YouTube been? It doesn't take that long to microwave.
It does take that long to microwave.
Well, actually, we microwaved it for too long and it exploded everywhere.
Wait, what is that?
It's case.
Oh, food.
Oh, yeah. Nice.
Okay. Who wants to tell me what this means? Guys, who wants to tell me what this means?
I want to tell you.
Oh, for all of X
So,
in the
dude,
natural
can you shut the
numbers.
hell up and let me talk? For all of X in natural numbers, X is greater than 2 implies that there does not exist a, B, or C value in natural numbers. Wait, what's that? Such that A to the X plus B to the X equals C to
This is Fermat's last theorem. Now, who wants to repeat what Joseph said in English?
I got you.
For all of
All right. Wait, that was English.
What I meant is like a more natural way. It was a joke.
Okay. I got you.
For all X in the natural numbers, if X is greater than 2, then there is no triplet A, B, and C in the natural numbers, such that A to the X plus B to the X equals C to the X. That is Fermat's last theorem. So like, for example, if X is 3, there is no such pair A, B, and C, such that this is true, where A, B, and C are natural numbers. Does not exist. Okay. Now I'm going to erase all this.
Oh, they proved it, didn't they?
Yeah, they proved it. You guys are
Yes, they proved it in like the 80s or something. This is just big picture type stuff, like allowing you to see the relevance. Okay, guys. Okay. Guys, I have another one. That wasn't the entire club, guys. Okay. For all epsilon. Wait, that's a 3. For all epsilon in the real numbers.
That is one ugly R.
This one's a bit harder.
Wait, don't you just take a derivative of that thing?
Dude, no. What the heck? This is much simpler than derivatives. I'll tell you that.
What do you want from your plate, Eli?
Dude. I'm cool.
Oh, I see.
He's recording, by the way.
Okay, who wants to tell me what this is? Who recognizes what this is?
Oh, I recognize what this is because I used to start taking calculus.
What is it?
Oh shit. I mean, it's the proof for like the equation for I don't know.
It's
Wait,
a
wait,
limit.
let me
It
try.
says that for all epsilon, that's the y. That's the y deviation. There is a delta such that whenever x is within delta of c, such that whenever x is within delta of c,
Wait,
then
why
f
is
of
it
x
like
is
an
within
8 now?
epsilon of L. So that means pretty much. So that means pretty much like
I need
no
more.
matter
This
how
is
close
not-
you want y to be, to the limit, you can find a tiny range of x's such that that's true. Such that y is in the right range. Okay, that is the definition of a limit. So this is all review of last week.
Whoa.
Now we're gonna get going. I'm gonna talk about some sets stuff. So there's two ways to define sets. You guys already pretty much get the principle of sets, right?
Yeah.
They either contain things or they don't contain. Like for anything, it either contains it or it doesn't. Like it's pretty much the equivalent of a predicate from last week. You guys remember those?
Yeah.
It's a function, it takes in an object and then it gives out a Boolean. So you give it cat, it says no. You give it dog, it says yes. You can actually construct a set saying x in the universal set such that some predicate p of x. So then this is the set of all x for which this is true.
Wait, what's
Set
the
builder
universal
notation.
Yes, that's set
What's the
builder
universal
notation. Thank you.
set?
And this is what they call roster notation. What's the universal set? It's the set of everything.
Yeah.
Like
Does
all
it
natural
include-
numbers, all real numbers, all complex numbers, whatever it is you're dealing with, the universal set is the set of all of them.
Does it include
Wait,
the
can't you use
universal
a
set?
backslash at the end of a set to indicate that you excluded some numbers?
Okay, I'm going to talk about that. We're going to talk about operations in a bit. But yes,
Wait,
that is
why?
correct. A backslash or a minus. They also accept minuses. Yes, Sohan?
Wait, does the universal set include itself?
Ooh.
No. Okay, we're not going to go into the
Chicken.
contradictory stuff. But like, anyways, if you're dealing with sets, then I think there are sets that contain themselves, yes.
I don't think
Even when you get into infinite sets, yeah. Because you say L of 0, which is an infinite set, plus 1 equals L of 0, so that, yeah. Okay, never mind. Okay, so there are sets that contain themselves, that is true. So
I
the
think
empty set, this is the equivalent of saying for x such that false. Like, so it's saying x such that, and then you say something that can never be true, and then that's the empty set. It's like, you could also define it like this, but I'm going to try and show the predicates, right?
Hey, that's my brain.
That correspond. So
Wait, why is there a 1?
now we're going to go over subsets.
Oh, okay.
Like you can say,
Delicious.
a subset is the equivalent of implication. Like you could say that x, so the natural numbers is a subset, right, of the real numbers, right? Because we can say that for all x in the natural numbers, x is in the real numbers. That is the definition of a subset. And another thing we can say is that if we can show that there is a real number that's not in the natural
Wait,
numbers,
should that be an arrow
then-
that applies?
what?
The colon, should that be an arrow?
Well, it's saying for all. We're using the quantifiers. So
Okay, I'm getting those mixed up.
we can also say for all x. Another thing you can do is like you could do that. You could say for all x, if x is in this, then x is that. But you need the colon in there at some point. Usually we just lump this part in here, and then the whole part we're assuming that is like that.
And
Okay.
what's that symbol to see what the line under it means?
That is
What's
a
the one-
subset. That is the natural numbers are a subset of the real numbers.
Oh,
And another thing we can say is that they are a proper subset. You know how we have less than or equal to, and then we have less than, which
It
means
goes
that it's
to
not equal to. Like when we remove the bar underneath, that means that it's not equal to. This is a proper subset. We can say that this is a proper subset of the real numbers if we can show a real number that's not in the naturals, and that it's a subset. So like it's a subset of R is a proper subset of R is a subset of R, so all of its elements are contained in R, but R has elements that aren't in it. Like 1.5 is not a natural number, but it is a rational number. I mean, it is a real number. Rationals are Q. Okay, not R. Any questions?
Oh,
Yes.
for the natural numbers, I think the bar goes across the middle. Oh,
Does it?
yeah, I looked it up. Probably.
Okay, good job. I'm gonna continue writing it like that.
Oh.
Consistency.
Sure.
Okay, consistency is key. So now I'm gonna talk about some curly P. I'm totally butchering it, and then I'm gonna say of the natural numbers. And so what this is this is the power set, and you're like, wow, maybe this is too big to exist, and everybody's like, couldn't this lead to some kind of contradiction? Is it too big to exist? Because you'll see. So it's the set of all possible sets of natural numbers. This is the power set of natural numbers. And they have this for every single set, it has a power set. And there's a fancy property in like ... And then it also, all power sets contain the null set or the empty set, right? You get why, right? Because the empty set is a subset. Does that make sense why? Why the empty set is a subset of any set? Yeah. Okay, so power set is the set of subsets. Now for the Cartesian product. We're going to say the Cartesian product of natural numbers is the set of pairs. Oh wait, why did I just do that? Of pairs such that, or well actually I'm going to do a different set here. I'm going to take the Cartesian product of the natural numbers and Booleans, 1 and 0. We're going to talk about Booleans later. Okay. So this is the set such that it's the set of pairs of A and B such that A is in the natural numbers and B is in 1, 0, right? Yeah, see? Make sense? It's pretty much just like pairs, like X, Y pairs and stuff like that. So another notation they say is like for when you take the Cartesian product of multiple sets, like this, and like if you say n cross n, and then you take the cross of that with n, then it's really just an ordered pair of 3. So I don't know, we just call that n to the power of 3. So the Cartesian products actually do part, like this is the set of all 3D points that are actually, never mind. If you made all these R's, it would be the set of like 3D points in space. Here, it's like all 3D points on some kind of grid. Such that they can only have natural components. Like 5, 4, 3, that would be a good point in there. Okay, so there's some other operations that you can do with sets other than power sets and Cartesian products, because those produce other sets, right? Well, these operations also produce other sets. So we're going to talk about unions. So the union of set X and set Y is the set of elements, let's just say V or something, such that V is in X or it is in Y. So it includes everything that's in X and everything that's in Y.
Can you not write X like so V is in X, V, Y?
What? In X, V, Y? What? This is or.
Yeah.
Oh yeah. Just so you guys know, you remember this boy?
Yeah.
That means or.
Yeah, okay, but
It's taller than the other V's because it's actually not a
so
V.
you can't say
Okay.
you can't say V is in X or Y. You have to say V is in X or V is in Y.
Well,
just
dude, I'm not reading out the notation. I'm like V is in X or V is in Y. Like you can talk in English. Mathematicians won't judge you for that. They will. But you need to write it this way in logical notation. You can't say V is in X or Y. You would say V is in X union Y. That's what you would say. When you're talking about sets, instead of Booleans, there is a relationship with predicates here. But when you do unions, when you do sets, you need to call it a union, not an or. Same thing, same principle, you have to call it an intersection, not an and with sets. So that is this all v such that v is in x
Do you need to mention v on the left
and
side?
v is in y, right?
Wait, so what's it called again? Not union?
And this was what Kevin was bringing up earlier. I think it was Kevin. Okay, there's another thing we can do called.
Do you need to mention v on the left side of the equation for those two sets to be equal?
V? No, this is v. This is an arbitrary v.
It's just
and
the
then you
constant.
say in here.
First one is union, the second is
We could say this is in the. Remember how I was saying in the universal set? This can be anything. This v can be anything, such that this is true.
This sounds suspiciously like
It's
yeah.
a,
It is.
It is. Why do you think MIT calls this math for computer science? Like
Exposed.
literally, it is. Okay. So now we're going to talk about v minus y.
X minus 1.
V minus x minus y. V. So now we're gonna have v, right? And we're gonna say an arbitrary v boy, right? So we're gonna say that v is in x and v is not, or no, and v is not in y, right? That's the not symbol. And you need to put it before the statement. So, and not v is in y. Okay. Okay. Right, guys?
What? Well, what is this?
X minus y is the set of all elements such that they're in x, but they're not in y.
Oh, okay.
So, like if and it's also x backslash y, I believe. Like that was what Kevin was saying, right? Where'd Kevin go? Where'd he go?
Y'all go to MTY, they'll teach you that.
Okay, well, anyways,
I
look
go to
at this.
MTY, they teach
Wait, is
you.
it in calculus?
If you go to MTY, they'll teach
License
you.
algebra 2.
If you go to MTY, they'll teach you about triangles of attitudes.
What?
Okay, guys. But anyways, back to this. We could say the real numbers and like the real numbers slash 0, and we could say that is the domain of 1 over x, right?
It's like a playground.
That's the domain of 1 over x. It's
Yes.
real numbers without 0.
Yes.
Okay, now we're going to completely forget about that stuff, that set stuff. And I'm going to talk about something that I forgot to talk about last week, but it's more appropriate this week because we can get it all over with at once because there's analogous stuff for sets too. So, what does this mean? Everybody should not be like, ooh, on this one because it's like school stuff. What is this?
Hey, that's
Who can tell me it expanded? Say it.
For the
That's no. 0 plus 1 plus 2 plus 3 plus 4 plus 5, right?
But then there are 6 terms then.
wait, but that is
That is true. It goes from this one to this one, right? It goes from A to B. Okay.
Yeah.
So what we could also say is we can say,
It's like a for loop.
guys, what we could also say down here is this is gonna sound super extra, but look at this. We could say n in the set of x in the natural numbers.
Can you just say
Such that, dude, okay, we could say n in the set, I'm going to extend this. So, n in the set of x of natural numbers such that they are 0 is less than or equal to them. Joe, you're not helping. Okay, such that, okay, so n, we're going to sum over n such that they are in the natural, like n in the set of
Is 0
natural numbers such that 0 is less than or equal to x and x is less than or equal to
So
5.
when you put on the
0
top,
and
This is the same thing. This is that range from 0 to 5 that we summed over here.
Professor Eli.
Yes.
Can you just take out the stuff from the brackets and just replace x with n? Like you have to say n
Well,
is in
I mean,
x
no,
is
you
in
can't
x.
just do the bar down here. Nobody's gonna have any idea what you're talking about. But you can do this.
So then what
It's
goes on the
a
top?
bit extra. Okay, watch this. This is the loop variable.
Eli.
N.
Eli, you
Yes.
put anything on the top?
What?
You put anything on the top?
Nothing.
No, you don't.
Whoa.
Because the set is completely
See,
specified
as
here.
as
Here you have to say the beginning and the end here, but this is the whole set. It's all defined down here,
But it's
right?
not balanced. It's
It
not
is.
balanced.
It's not what.
Okay,
It's
so
not balanced.
That's.
What?
Dude, doesn't need to ignore this. There is no up here.
They
There's
just
there
snap
it is
it, just
balanced
erase
over
it.
here.
Just erase it easy.
Guys, you want it to be unbalanced? I'm gonna delete
Oh
this.
my God.
And stop Stop. Okay, long sigma. Okay.
Because summation.
What?
Does X always have to be in the set of natural numbers?
No. You can sum over other things, but I will tell you, if you do something like this, okay, what is this?
It's right.
What is this? You guys know how to do intervals?
Yeah.
Here's what this is. It's 0 plus 0.5 plus 0.75 plus 0.3 plus 5 to the negative 1 plus literally all numbers in this range. So if there's not a finite number of these things, then it's going to be some insane boy that you don't want to deal with. It's probably, in this case, it's infinity, right? It's all, literally, you're adding all numbers from 0 to 1. That's why we use integrals instead of, we don't add an infinite number of things. That's what we use integrals for in calculus. Because we make them infinitely small and we add an infinite number, and then it's like, okay, balances out. Yeah, that's a really bad explanation. But that's not what I'm teaching, so who cares?
Are you qualified?
Alright, so now, am I qualified? Okay, now I'm going to talk about something. Same thing here. We're going to draw a big one. This is bigger than the order we normally use. We're going to say n equals 0 to 5. And we're going to say is odd of n. And what is that?
What?
That says 0 is odd, or 1 is odd, or 2 is odd, or 3 is odd. This is repeated addition.
Oh, that's like repeated Booleans?
Yeah, this is repeated Booleans.
What?
Repeated ORing. It's repeated ORing. This is repeated ANDing. Okay,
What's going
this is repeated unioning for sets. You could say, oh wait, no, you can't union sets. Oh well, actually you can. You could say n equals 0, and then you could do the interval of like from 0 to n or something. And so then the end result was you keep unioning it, and then you get 5. And then like if you do the union, let me ignore this. If you do the repeated union from n equals 0 to 5,
That's not the union sign.
intersection. Sorry, that's the repeated intersection. Okay, then that would be what is included in 0, 0, 0, 1, 0, 2, 0, 3. What is included in that?
0, 0.
Yes, 0. We're not going to say 0, 0 because that's kind of dumb when we can just write 0. Well, no, it's the set of 0.
Oh,
Makes
so
sense? It's the set of 0. No,
What?
it returns itself.
I don't know.
What is that supposed to mean? Okay, anyways.
on? I have a question.
Return
Yes.
from it.
Wait, what's the first thing with the v and the n equals 0 and 5 thing? Like if you go all the
The
way
V,
to the
that's
top.
OR. Do you not remember logical OR?
No,
So
like
what do you do with that?
yeah, like
Okay,
the
that is either odd of 0 or odd of 1 or
Yeah, so
odd
no,
of
no,
2
So that's true then, right?
or dot dot dot. And the thing is, this is true.
So the
So
whole
that
thing
means
is
all of them
true.
are true because it's OR.
So then
So
that
it
thing would
This
all
whole
be true.
thing is true.
so it returns a boolean.
So it's a
Yes, it returns a boolean. This returns a boolean. This returns a boolean. This
Those two
returns a
return
set.
sets.
This returns a set. This returns a number. Because the thing is, plus acts on numbers. So this gives a number. Like plus gives a number, so repeated plus gives a number. Or gives a number, so repeated or gives a number. And gives a number, yeah, whatever.
And don't forget.
I mean, no, it doesn't give a number. Or gives a boolean. So this gives a boolean or a predicate or something. I don't know.
And don't forget pi.
Okay. Anyways,
The repeated multiple.
moving on.
One type.
Anyways, does it make sense? That was a really bad explanation.
It makes sense.
It makes sense.
Okay.
And has like
Long sigma has been erased. Okay. I don't think we're ever going to get to everything. Okay. So now we're going to talk about functions. So, hey, who knows what the vertical line test is?
Oh, it's where you can check if it's a function of
No, that was rhetorical. Don't all answer at once. Oh.
You should encourage collaboration in your class.
Dude, that's like everybody on the Chinese culture presentation yesterday assignment. Miss Lee was like, record 1 minute and 30 seconds of audio, and then everybody's like, for the whole like 1 minute and 30 seconds. And that's like literally what it was. Okay, so a function, we have f of x, right? It's a relation from one set, a, b, c. This is the set of C. Usually this means complex, right? But right now it means characters. It means characters. Okay, that is what real mathematicians use it for, i.e. me. Okay. 1, 2, 3. This is going to be the set of 1, 2, 3. I don't know.
Are you going to do like 1 to 1?
Okay, look at this. So there's a function that gives the order of it in the alphabet. And so what we can say about this function, or any function really, I'm going to define is that the vertical line test must hold. And what that means is that for all A in like the original set, right?
Domain. Is it the domain?
No. Well, I mean the domain is that
It
gets
is
a
kind
bit
of the
confusing,
domain, right?
I mean it gets a bit confusing, but anyways, for all A in A, there exists exactly one B in B. So that means
You know what that
So
looks
for all
like?
A-
Like someone who
what?
doesn't know anything about this class.
yes.
Ooh.
No,
What?
there's no way to misinterpret that. Okay.
What
were
you
such
trying to get
that,
at, Joseph?
dude, such that
Okay, it looks like you're right.
F of A equals B. So that means this is the vertical line test. For F of A, there has to be a B.
Wait,
And
is
there
that-
can never be more than one B.
Okay,
There's
that's
exactly
not
one B.
possible. Is
That
that
is
a
the
special-
vertical line test.
Is that like a special C? Is it like John?
Well, yeah, I did the math BB thing, you know? It's the special font that they use for sets. Okay, never mind.
No. The like
Be like-
lowercase b, it like looks weird.
No, it was not
Yeah.
special.
Oh, so it's just your handwriting?
It's only special because my handwriting is special.
Whoa.
Eli,
You're also
Yes.
special.
but that doesn't mean for every element in B that there's only one element in A, right?
That is
That's the
true.
definition of
That
one
is
to
the
one, right?
definition of injectivity.
Oh,
I was going to
okay.
bring that up third,
Holy
but I will
balls.
bring it up now.
Can we bring it up there?
Injective. So it is injective or
Yeah.
1 to 1, I think. Yeah.
Yeah.
They're really confusing. Okay, so
I think the other one is
injective.
like onto, right?
Dude, shh. Okay, for all B in B, this is not true of all functions. This is only true of some functions. There exists exactly one A in A such that f of A equals B. This is not true of all functions, only injective functions.
Okay.
So like a line with a slope of not 0.
Yes.
Yeah, pretty much. That's true.
So and like a cubic function, right?
Yeah.
That
Yeah,
doesn't
pretty much,
doesn't,
yeah.
doesn't like
Dude, cubics are really nice. They're like invertible and stuff.
But not all cubic functions.
yeah, not all cubic.
Well, yeah, but the x cubed, you know.
Yeah, actually.
Okay. Well, anyways, they're really nice. Okay. Okay. So it is 1 to 1. Does that mean this function has an inverse?
Yes.
Yes.
No, it does not. Because it is not surjective. So what this means?
Nice.
What's
Or wait, no. I'm just
You're
gonna
holding
say.
an eraser.
Okay, so here's the thing. This is injectivity, right? I'm sorry, I did not mean to put exactly one. This is surjectivity, which means that for all B, there exists. Oh wait, no, mind. This is
What?
okay.
You're holding an eraser.
Teachers
Okay,
confused.
so I'm gonna talk about this. I'm gonna fix this up. Okay. So for all B and B, if there exists an A in A such that f of A equals B, then there exists only one. So that says if it exists, then it's the only one, right? Like if the inverse exists, then it is the only one. Right?
Okay.
But that is injectivity.
Okay. What?
I'm practicing my medical handwriting.
What?
Okay.
That looks
My
nothing
doctor
like.
handwriting.
That looks nothing
It
like.
looks like Christopher Wu.
Okay. Now, guys, now I'm gonna do surjective. So surjectivity is when there exists an A for all B. So what this means, what surjectivity means, is pretty much all elements of B are in the range, okay? That's what surjectivity is. All what? I'm not good at writing on whiteboards, okay? Okay,
Good, you want me to write it for you?
No!
Guys, I'm watching.
Well, because it's double S.
Order! Okay, surjectivity means that all numbers are in the range. Injectivity means that, like, for example, a parabola, this is not injective because its inverse does not pass the vertical line test.
Oh.
So that means it is not injective. Like there is, if you choose a certain y, there's multiple x's, not injective. For surjectivity, like let's say you have a cube, that means that for all y you can find at least one. Bijectivity is when both of these are the case. That means there is exactly one a for all b, right? And so when it's when it's bijective, that's when you have an inverse function, okay?
Oh, I got it.
And you guys know what inverse functions are. I don't have to you guys can infer that. Okay, so so guys, summarize. I just want to make sure you all understand. Like what is surjectivity?
You, they found out. Surjectivity is when I'm not sure how to use it.
Okay,
It's when you
it's when the range is
21.
it's when the range is all possible outputs. It
Wait,
reaches
wait.
all possible outputs. And what is injectivity?
Wait, okay, which
When
one
the
is
domain
one
is
to
all
one?
possible outputs.
What?
When the domain is all possible outputs. What?
No.
No.
Dude, no,
That's
the domain is always all numbers, okay? That's the definition of a function. It needs to be true for all numbers.
Well,
Well,
also,
not
there's
necessarily,
for
right?
all imaginary
Like it needs
numbers.
to, well,
Like you can
yes,
define it.
dude, otherwise it's a partial function.
Wait, what
Like
do you
1
mean
over
by-
x, you call
mean
that a
only
partial, that is not a
piecewise-
function from the
Wait,
real
do you mean
numbers.
all
okay.
numbers?
What about piecewise
Or
functions?
all-
What about piecewise? They're just fine. Yeah.
Wait, Eli, I have a question.
They're lit.
What even is injectivity?
Okay, it is injective if whenever
You can inject.
there exists, like whenever y equals something at a certain x, there is no other x such that it has the same y.
Oh.
So that means pretty much this is problematic. You see how there's two of these? This is problematic in creating an inverse. So this is not injective.
Okay.
This is injective because we can say if we draw a horizontal line at any point, it only hits a maximum of 1.
Oh, so it's
That
like a
means it's
horizontal
injective.
line.
As opposed to a zero.
What?
Never mind.
Okay,
Wait, so
here's
what's
another good
bijectivity?
example. So you know e to the x, right? It looks like
Yeah.
this. It is injective, meaning for all of them where it exists, there's only one, right? But it is not surjective because it doesn't cover the negative numbers. There's none down here.
Oh, I
Yeah.
see.
Okay,
Wait, hold
moving
on.
on.
Eli.
Yes.
Oh,
Wait, so
big guy.
square root functions start at 0. Would that be a partial function?
Yes, that's a partial function. Square root. Remember, when your teacher says f of x equals root x, and then they talk about like graph this function, you should be like, that's not a function.
No, you shouldn't be like that. You should respect your teacher.
No, like that's
Wow.
the joke. Okay.
You let your
And also, it's beyond the scope of most high school classes.
your handwriting.
Dude, yeah, well, high school classes shouldn't be wrong because of it. Okay, anyways, yeah, roasted. So now we're gonna talk about something called. Okay, who knows what this is?
Tha.
F of n. Oh, that's
Oh, it's physics.
That's a recursion.
Physics.
Oh, that's a recursive function.
Fibonacci.
Fibonacci
Guys, it's
series,
Fibonacci,
yeah.
except it's missing one thing. This is what we call a recurrence.
There's no
It's
base
defining
case.
it using.
That's gonna give you a stack overflow.
Yeah, okay, there is no, like Joe said,
There's no initial value.
there is no initial value. That's what we actually call them. Wait, no. They call them initial conditions, sorry.
Close enough.
It is missing the initial conditions, f sub 0 equals 1, f sub 1 equals 1, right?
Wait, isn't there an explicit
Eli.
formula for
Eli.
that too?
Well, that's what we call the closed formula. When we have both of these, when we know both of these things,
That's
this is a
three
closed
things, by the
formula
way.
since it defines the whole function, all of it.
Oh.
Okay, now moving on. It seems like since you guys all went, oh, that means you understand it.
Oh.
In my mind.
Oh.
Okay, So, in other words, just go oh whenever I say something.
Yo.
Okay, so we're going to talk about the cardinality of sets. What is the cardinality of 1, 2, 3? We're bringing up that set stuff again.
It's 3, right?
3.
Oh, that's just the size, right?
That is the size.
It's
okay.
like arrays dot length, right?
Okay, I just want to say,
size.
look at this. I'm going to say 1, 2, 3.
You have an
What is
array
the
size.
relationship?
Second eraser, Eli.
This is A, B. Okay, and then this is A, B, C, right?
You know, Eli, I want to see.
Okay,
what
and
it
I
looks
want to
like.
say, what is a way using a function from A to B that we can tell if they are the same size? Okay.
Just use a for loop and count the size of each one.
Here's the thing: if there is a bijection, that means all of these have a every A has a corresponding B. That's because it's a function. Every A only goes to one B at most because it's injective, and every A has a B, and every B has an A to pair with. That means it's surjective. Those are all the properties of bijective functions that are in the definition. From those, we can determine there's a one-to-one pairing. One-to-one is used to mean injective, but that's super confusing because it really seems like it should mean a bijection, right?
Yeah.
But instead, one-to-one only goes one way. But anyways, so if there is a bijection, remember those bijections from set A to B. A and B are the same size, yes.
Are you sure you're not like left-handed? Because your handwriting looks like you're left-handed, but you're trying to write with your right hand.
Wait, what did he
Dude,
just
my
say
left hand
about
is much worse. You want me to write the next thing with my left hand?
Yes,
yes. I will, dude. Okay. So, if there's an injection, wait. Okay, if there's an injection, which means that.
No.
Oh wait, sorry.
Eli, it's fine, I'm good.
Okay. If there's an injection, right?
Goes from 0 to negative.
No, that's not a 2, that's a C. Okay, guys, order in. Guys, we're never gonna finish. Okay, guys.
You gotta go.
We do? What time is
It's
it?
5.
Oh, crap.
Dude, no, we have until like 5:15.
Yeah, but we have to leave the parking.
Okay, guys,
Oreos.
Almost the 50.
I'm gonna continue lecturing. Who's running the recording? Wait, Joe, are you leading?
Wait, why is it not recording?
Wait, it's not recording?
It's recording. It's recording. It's got
Okay.
it's fine.
Okay, guys. So, if there's an injection from A to B, which means a function such that, well, actually, I'm going to say A, B, C, D, right? If there's just an injection from A to B, that means that, which means you can choose a B for every A, such that no A's have the same B, right? Like, no two collide, per se. None of them collide on the same B when you like each of them has its own B. Some of them aren't chosen, but that means that the size of A is less than or equal to B. If there's a function like that that's injected from A to B. And so what we can say is that if there's an injection both ways, and I just want to say when you invert an injection, that's a surjection. They're like the opposite thing.
And then you get a bijection.
Okay.
Bye-bye.
Wait, where the word?
Okay, so but here's the thing. If there's an injection this way and an injection that way, then both of these things are true. And so I can just say that they're equal, right?
Yep.
That is the Schroeder-Bernstein theorem. All the people that actually cared just left.
Oh, it's just us.
Okay, and so then another thing, I'm not even going to prove this because this is a whole pain, but you can look it up and I'll help you understand if you want. The power set of A, let's say the power set of 1, 2, 3, like, look at this. It is the null set, set of 1, set of 2, set of 3,
Set of 1 and 2.
really? Okay, set of
2 and 3.
Hey, that just shows I read the textbook. Like 5
Bro,
months
you
ago.
can't eat that many Oreos. Just like
1, 2,
30.
3.
Well,
Okay, guys,
sir.
let's count these. Okay, so there's 3 here, right? Let's count all these. There is 1, 2, 3, 4, 5, 6. Wait, no, that's those. These are the same element. Okay, 5, 6, 7, 8. That is 2 to the third, right? So the number of elements in A is 2, or in the power set of A is 2 to the power of the cardinality of A.
Wait, Eli, can we eat this, or is this like in the bag, but we're not supposed to eat it?
Oh yeah, you can eat it.
Oh, okay.
Guys, don't freak out. Okay, guys. So you guys see this? The size of the power set, which is the set of all possible subsets, is 2 to the power.
Well, you said a bad word.
No, I didn't. What
And you said wa instead of like wa.
No, you said wa, which means O-F-B.
I know.
Oh, really?
Thank you. No, but he said wa.
Silly
So we're just gonna
American.
ignore it.
No,
We're
wa
gonna say
means O.
he just can't oh.
Yeah. Wa means O. It's like, if I said O-F-B, that means wa cao.
Okay.
Okay, guys. We're not going to discuss Chinese cuss words. We are going to discuss infinite numbers. So in calculus, remember that calculus example from earlier?
Oh no.
What calculus?
Wait, oh, you mean the
Okay,
extensions?
so no, I'm not going to talk about calculus. I'm not going to teach you about calculus today. I'm going to teach you how lame calculus is. And I'm going to show you, Miss Ring was like appreciating this because she talked about that a lot last year.
What did I talk about a lot?
How lame calculus is compared to stats.
I never said that. I
Yeah,
just said
that's not even true.
statistics is underrated. Statistics is unjustly underrated. I did not discount you.
Okay, so in calculus, they don't like dealing with big numbers like infinity or little numbers like 1 over infinity. So what they do instead is they deal with limits. You guys know limits?
Oh, I
talked
know
about
that.
limits.
I learned that.
So you say this is true for all numbers after a certain point. Like you can get arbitrarily close to this. But here's the thing.
I need more cupcakes.
You already have like a dozen orders.
So, but in discrete math, we're actually going to use infinite numbers. Isn't that cool? Isn't that cool?
Ow.
Okay.
Oh man.
Do you want to taste of the elephant?
Wait, yeah, sure.
So we're actually going to use infinite numbers. So I already talked about the how to do the cardinality of a set, but I'm going to tell you something. The cardinality of the set of real numbers, what is that? What is it?
Infinity.
It is Aleph naught. And you can draw that by doing a straight line down and then doing some kind of like x cubed crap.
Wait, what?
And then you say 0, sub-0. That is the smallest number that is bigger than all natural numbers.
What?
Because wait, okay, so think about this. So the size of the set 0 is 1, right? Then the size of the set 0, 1 is 2, right?
Yeah.
So it's 1
Is that
greater. So the
cardinality or
cardinality of
absolute
the set,
value?
the cardinality of the set of numbers from 0 up till n is n plus 1. So Aleph naught is the largest natural number plus 1. It is the smallest number, except that number doesn't exist. But it is the smallest number that is bigger than all integers. Okay?
So, like,
And so if we take the
plus
power
1.
set of all the natural numbers, and that means all possible sets of natural numbers, so the null set, 1, 2, 3, comma, 4, and then like the set that just has 4, 20, 69 in it. Okay.
That's funny.
Okay, so okay, that's the set of all possible subsets of the natural numbers. Finite subsets. Because when you get infinite subsets, that gets a bit weird. So, anyways, so here's the thing: the size of the. Now, what did I say about the cardinality of the power set?
Absolute value.
It's infinite.
Infinite.
No, what did I say about the cardinality of a power
X
set?
zero.
Okay, 2 to the
2 to
Oh,
the
two
power
that.
of that, of the cardinality of this.
Oh, the
So
cardinality.
this is 2 to the Aleph naught, right? Or wait, no, I drew it backwards. That's chi.
What's
The
Kai?
stat.
You have
It's,
an
you learn about it in
eraser
stats.
in
Is that the dude from Ninjago?
Okay.
Oh yeah, I know that guy from Ninjago.
Okay, guys.
I have
So
one
it's 2
of
to
them.
the Aleph naught. Well, here's the thing. This Aleph naught is also Beth naught.
What's
Wow.
that?
It's another sequence of numbers. So here's the thing: 2 to the Aleph naught we say is Beth sub 1. And
know,
2
it's
to the
like a
Beth
hammer
sub
and
1
circle.
is Beth sub 2. And so pretty much here, you just keep on going and doing, it's like the left side of a rectangle. So
Wait, what's
here you just
that?
keep on going 2 to the power of.
You're like, what's the Beth? What's Beth?
I'm explaining what Beth
Oh.
is.
Wait,
So
Alice
this is the
looks
sequence
like a-
of Beth numbers, right?
Yeah.
These are all Hebrew. For some reason they ran out of Greek, so they started doing Hebrew for discrete math.
Oh,
We
yeah.
got dissed if you ask me.
Well,
But,
no, our
We should use
Roman-
English characters.
200 IQ.
Well, they already used
Wait, dude, we
Roman.
use E. We use E.
They already used Roman. They went to Greek, so they had to go.
Yeah, dude.
Oh,
Wait,
we
we
should
use
use
upside down
Chinese
A's and backwards E's and
characters.
everything. Okay, guys.
Let's use Chinese characters.
Yeah, you can do.
No.
Okay, guys. So you can keep doing this and making bigger and bigger Beth numbers. You raise it to the power of 2. And here's the thing: the way we define Aleph 1, it's the smallest number that's bigger than Aleph naught. But here's the thing: there's something called the grand continuum hypothesis
Oh wait, this
That
is
says-
a useless one, right?
that says Aleph n equals Beth sub n. So this is like the one where you keep doing 2 to the 2 to the 2 to the 2 dot dot dot. And then this is the one where you say like greater than, greater than, greater than, greater than. Right? A num. So Aleph sub 1 greater than Aleph sub naught, but it's the smallest number that's greater than Aleph sub naught. So we can say Aleph sub 1 greater than Aleph sub naught, and for all x greater than Aleph sub naught,
Wait, did you draw the x's backwards or no?
then x is, then x, wait, maybe I haven't, okay, yeah, that's the right way. I'm sorry, I've been drawing
Oh,
kind
it
of.
looks like a
It's
hammer and
confusing.
sickle.
Okay, so x is greater than equal to Aleph sub 1, right? So if it's greater than this, then if it's greater than Aleph sub naught, it's greater than or equal to Aleph sub 1. So it is,
Okay.
Aleph sub 1 is the smallest number that's bigger than this. And so, according to the grand continuum hypothesis, it says that
Oh,
it's
shit,
also
my sugar's
equivalent to
crashing.
2 to the Aleph naught. So like 2 to the Aleph sub n equals Aleph sub n plus 1, which is equals the biggest number, the smallest number bigger than Aleph sub n. So these are all infinite numbers we're dealing with, and for all intents and purposes, you can just say that's true. Like, it's literally impossible to prove. Remember how I was saying there's certain things that are true that are impossible to prove?
Mm-hmm.
This may be one of them.
What else is
What do you
one?
mean,
Like
wait?
1 equals 1? Wait.
What?
Wait, how do you prove that 1 is 1?
It's an identity.
Oh,
That's-
wait. But like.
Okay, guys, we're not going to prove that in discrete math class. Okay, so now you have a basic idea of the Aleph numbers. You can Google how arithmetic with them works. Pretty much, if you say n, where n is less than or equal to Aleph sub n, right? And then you say to the Aleph sub n, right? What that's going to give you is Aleph sub n plus 1. And it doesn't have to be 2. This could even be Aleph sub n minus 1, or even Aleph sub n, I think.
Yes.
Yes, that's true. Okay, yes. You could do Aleph sub n to the Aleph sub n. Pretty much when you say, when you're dealing with infinite numbers, x to the y equals, so if x is greater than y, then it's x, right? But if y is greater than x, if y is greater than or equal to x, then it's actually y, it's 1 bigger than y. Okay, that's actually how it works. That's going to be on the Kahoot. You don't actually have to know that crap, but I put a question on it in the Kahoot, so that's why I'm teaching it. Well, you do need to know infinite numbers. You don't need to know the arithmetic rules. Those are complicated and no mathematicians know them. I'd probably butchered them. Okay,
You're teaching
so here's the thing. Aleph sub naught, that is the size of the natural numbers, right? Why do we call that grand continuum hypothesis the grand continuum hypothesis?
Because it's grand
Because
and
it
it's
says
continuous.
it insists that aleph sub naught is beth sub naught, right?
Yeah.
But aleph sub naught is just beth sub naught. They like start at the same point.
Alright, so how does this
Anyways,
help us
so
in
aleph sub
life?
1 equals beth sub 1. That is the grand continuum hypothesis. And the reason being because beth sub 1 is, surprise, the continuum. It's also called the continuum, which looks like the cool S, but it's a C, and it is the size of the real numbers. Okay, that's the continuum. Continuum. Awesome. Okay. And so another way of stating it is just this, because then everything else can be proven inductively, that aleph sub n equals beth sub n. Everything else can be proven inductively. We're going to go over induction later.
Oh, wait,
Not
that's
today.
the thing where
Definitely
it's
not
like
today.
you have to
Okay,
do SC
now
plus one.
matrices. Okay, you guys know matrices, right? You just like how to multiply matrices. You just take this and you
Wait,
like
those are called
multiply the row and the
arrays.
column. Okay, if you don't know that, I'm just like not going to explain it.
Are
It's
they
like,
called
we don't have
arrays?
enough time. No, we do not call them arrays.
Aw.
Okay, so what we're gonna, the structure is actually significantly different than 2D arrays. There's a lot of things matrices do that are like really freaking weird. If you just put in like, don't make any sense at all if you just put random data in it, like a 2D array. But there's actually, you will use this in comp sci. I used my knowledge of linear algebra on a UIL test last year, and I'm still flexing it. It was awesome.
Dude,
It felt amazing. Okay, it was like this conditional probability matrix, and you just like multiply them using matrix multiplication. Well, anyways, so when you say this, it's a sub 1, a sub 2, a sub 3, and then b sub 1, b sub 2, b sub 3. That means that the element in the resulting matrix, c sub 1, 1, right? That's going to be c sub 1, 1 equals a sub 1, b sub 2, b sub 1, plus a sub 2, b sub 2, plus dot, 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 through the whole row, right? Well, for Boolean products, these are all going to be 1s and 0s, right? Okay, 1, 1, 0, 0, 1, 0. So what's the equivalent of multiplication for Booleans? It's and. Joseph, you should know that. You need to know that for UIL.
Oh, I do? Oh,
Yes,
crap.
they use it all the time. Like where they have the plus for or and then the
Oh,
they
yeah,
leave out.
yeah,
Okay, well anyways,
yeah,
a
that's
sub
true.
1 and b sub 1 or a sub 2, and then all these are in parentheses, sub 2 and b sub 2. You don't need parentheses around, it's just that you guys probably don't know the commutativity rules. I mean, the order of operations for these.
I don't know something.
That's very true. Okay,
What a
and so then or that. So then this is going to be a Boolean. And then all
You're
of these
a
are
Boolean,
Booleans.
man.
So that's how you multiply Boolean matrices. Okay, that is all I was going to talk about. Who wants to do a Kahoot?
Oh, me!
With just like 4
Yeah,
people.
I'm not keeping you late. Miss Ringwood,
Did the top 5 get a prize?
you're not staying here late because of us, right?
No, we're going to, my husband's bringing me dinner, we're staying for the game. When I go to the football game, I don't leave.
Oh, awesome.
So you're fine. Kahoot away.
All right.
Are